Welcome to EPA's online training series for the Water Quality Surveillance and Response System, or SRS program. This primer module provides basic information about the design and objectives of the Online Water Quality Monitoring, or OWQM component of an SRS, and describes how it can be used to detect water quality incidents in drinking water distribution systems. An SRS provides a systematic framework for enhancing distribution system monitoring activities to detect emerging water quality issues and respond before they become problems. It consists of 6 components grouped into 2 operational phases: surveillance and response. The surveillance components include OWQM, enhanced security monitoring, customer complaint surveillance, and public health surveillance, and are designed to provide timely detection of water quality incidents in distribution systems. The response components include consequence management and sampling and analysis, which support timely response actions that minimize the consequences of a contamination incident. In this training module, we'll focus on the OWQM component. The module covers 4 topics. Topic 1. What is OWQM? Topic 2. What are the major design elements of OWQM? Topic 3. What are common design goals and performance objectives for OWQM? And Topic 4. What are cost-effective approaches for OWQM? This training module will take approximately 12 minutes to complete. First, let's define OWQM. OWQM uses real-time water quality data collected from monitoring stations deployed at strategic locations in a distribution system. This data is continuously analyzed to support system operations and provides valuable insight into real-time conditions throughout the system. This information allows utilities to detect incidents of unusual water quality in sufficient time to take corrective actions if necessary. The data generated by OWQM can also support system optimization, regulatory compliance, and asset management. We'll cover these benefits later in the module. Now let's discuss the major design elements of OWQM. OWQM is composed of 4 design elements: data generation, data communication, information management and analysis, and alert investigation. While OWQM designs may vary, an effective component requires all 4 design elements. We'll discuss each design element in greater detail in the upcoming screens. The data generation design element determines the type of water quality data produced by OWQM. It's defined by 3 decisions. First, utilities must decide which parameters to monitor. The parameters monitored in distribution systems determine both the information available to utility staff and the types of water quality incidents that can be detected by OWQM. This monitoring can involve conventional parameters, such as chlorine residual and pH, advanced parameters, such as TOC and UV visible spectral absorbance, and hydraulic parameters, such as pressure and flow. Next, utilities must select which sensor technologies to install. The sensors used to monitor selected parameters, as well as the equipment required to install these technologies at monitoring stations, can dramatically impact the capital costs, operating costs, data accuracy, and maintenance associated with OWQM. Finally, utilities need to identify where to monitor. Monitoring stations can be located anywhere in a distribution system where there is an available supply of water, including utility-owned facilities, such as pump stations and storage tanks, city-owned facilities, such as fire and police stations, large water users, such as bottling plants and hotels, and stand-alone installations, often installed within a public right-of-way. The data communication design element involves the transmission of OWQM data to a central location for storage and access. Data communication solutions may include digital subscriber lines, cellular networks, radio, and city-owned wireless networks. The type and quantity of data produced, existing communication capabilities, and the locations from which data must be transmitted can impact the selection of these solutions. The next design element is information management and analysis, which we'll cover using 2 screens. Information management covers the process of receiving and storing data so that it's readily available to users. A variety of information management systems can be leveraged to support OWQM. SCADA systems can be used to display recent values of all parameters measured at a given monitoring location. More sophisticated GIS-based interfaces can be used to view the status of all monitoring stations at a glance. In both cases, Users can navigate within the interface to get more details on parameter values, alerts, and station status. The second aspect of this design element deals with data analysis. OWQM data must be regularly reviewed to support system operations and detection of water quality incidents. Data analysis methods vary in complexity and can include visual data review, simple setpoint alerts, and sophisticated computer algorithms. When a water quality anomaly is detected, an alert can be generated to notify utility staff. This time series plot depicts OWQM data that would likely trigger an alert. The vertical black lines on the right side of the plot identify a period of time in which both the chlorine residual and pH levels deviate from baseline water quality at a monitoring location. The final design element is alert investigation. When an alert is received, staff should follow defined alert investigation procedures to identify its cause. In many cases, a simple review of supporting information, such as operational data and maintenance activities, is sufficient to identify that an alert was not caused by a water quality incident. If a cause can't be identified through data review, an on-site investigation can be conducted at the monitoring location that produced the alert to determine if accurate data is being generated and transmitted. Water samples may be collected during these investigations to enable further analysis of water quality in the area. If it's determined that an alert was caused by a water quality incident, it may be necessary to take corrective actions to mitigate potential consequences. For example, if the alert was caused by low chlorine residual concentrations, steps may be taken to increase levels in the area. However, if a cause can't be determined, the possibility of system contamination can be further investigated using procedures in a utility's consequence management plan. Now let's discuss common design goals and performance objectives for OWQM. Design goals are the specific benefits that a utility expects to achieve as a result of OWQM implementation. A fundamental design goal of an SRS is the ability to detect and respond to water quality incidents in a distribution system. However, OWQM-specific design goals can also be realized. Examples include detecting unusual water quality conditions in distribution systems resulting from common system occurrences, such as nitrification, pressure transients, rusty or turbid water, treatment process failures, pipe breaks, and excessive water age, or the presence of foreign substances in systems resulting from leaky pipes, inadvertent cross-connections, backflow events, chemical overfeeds during treatment, and intentional contamination. Optimizing system operations by providing utility personnel with knowledge of real-time water quality that can be used to understand the impact of operational changes on water quality and hydraulic flow paths. This knowledge can then be used to better manage and operate the distribution system and treatment processes. Supporting compliance with water quality goals and regulations, as information collected throughout distribution systems, particularly in areas of concern, can allow staff to identify emerging water quality problems and take corrective actions to avoid compliance issues, and enhancing asset management, as regular data review can reveal changes in distribution system conditions that may negatively impact the condition of assets, such as pipes, pumps, valves, and storage tanks. Performance objectives are measurable indicators of how well OWQM supports an SRS to meet design goals established by a utility. Throughout design, implementation, and operation of an SRS, utilities can use performance objectives to evaluate the added value of each capability, procedure, or partnership. Specific performance objectives should be developed by utilities in the context of their unique design goals. Examples of performance objectives include incident coverage, spatial coverage, timeliness of detection, operational reliability, alert occurrence, and sustainability. OWQM supports these objectives in a number of ways. For incident coverage, OWQM helps to maximize the types of water quality incidents that can be detected. Water quality changes that can be detected by OWQM are determined by the parameters monitored. For spatial coverage, OWQM helps to maximize the portion of a distribution system that is monitored. The area monitored by OWQM is determined by the number and location of monitoring stations. For timeliness of detection, OWQM helps to minimize the time required to detect water quality incidents. Timeliness of detection for OWQM is determined by the number and location of monitoring stations, the frequency of data analysis, and the time it takes utility personnel to receive and investigate an alert. For operational reliability, utilities will want to maximize the percentage of time that OWQM is fully operational. This requires proper maintenance of all equipment and information management systems, as well as consistent implementation of standard operating procedures. For alert occurrence, utilities will want to minimize the number of invalid OWQM alerts generated while maintaining the ability of the system to detect true water quality incidents. Alerting is primarily impacted by the accuracy of OWQM data and the data analysis methods used. And for sustainability, utilities should design OWQM to realize benefits that justify the costs and level of effort required to implement and operate the component. Benefits are largely determined by the information produced by the system, which allows for day-to-day system monitoring and detection of water quality incidents. Costs include capital and ongoing costs, the level of effort required to implement and operate the system, and the level of effort required to investigate alerts. Collectively, the design goals and performance objectives established for OWQM provide the basis for the design of an effective component. The last topic we'll cover is cost-effective approaches for OWQM. Utilities can take a number of simple, relatively inexpensive steps to develop the foundation for OWQM, such as use distribution system water quality data already being collected, such as chlorine residual concentrations at utility-owned facilities. Consider building SCADA screens that display data plots or developing spreadsheets for data review and analysis. Establish setpoint values that automatically generate alerts when water quality anomalies are detected. Formalize procedures for routine data review, such as checking data at the beginning of each shift, and establish procedures for investigating OWQM alerts, and practice these procedures through training and exercises. You might discover that your utility already has some of these suggested capabilities in place. If this is the case, implementing OWQM will be much easier. Thank you for completing EPA's training module for water quality surveillance and response systems. If you would like to learn more about the design and implementation of an SRS and its components, additional training modules for each of the 6 SRS components are available on EPA's Water Quality Surveillance and Response website. If you have specific questions, please feel free to contact EPA